Okay, so now you're familiar with Kirchhoff's loop rule and Kirchhoff's junction rule, and those serve as methods we can use to double check our work when solving for reducible circuits. However, some circuits aren't reducible, and Kirchhoff's rules don't represent a way to double check our work. They represent the only way that we can go about solving the circuit. And here's one example. I don't see how we can come up with one single equivalent resistance for this whole circuit. You'd be hard-pressed to state what's the connection between this 5 ohm resistor and this 1 ohm resistor. Now, you could make a mistake and say, well, current flows through the 5 ohm and then goes off to the 1 ohm. They appear to be in series, but you miss the fact that there's a junction between the two of these. So no, those resistors most definitely are not in series with one another because they don't have the same current flowing through them. You might be tempted to say that the 5 ohm resistor is in parallel with the 2 ohms resistor because they're on two separate paths that get us from X to Y. However, there's also different batteries on those paths, and so the electric potential from points X to Y are the same. However, the potential difference across the 2 ohms of resistance is from point X, maybe we can call this point, I don't know, J, all right? And the potential difference across the 5 ohms is from Y to, we can call this point H. So, it doesn't seem like there's any guarantee that the potential difference across the 2 ohm resistor is the same as the potential difference across the 5 ohm resistor. So they are not guaranteed in any way at all to be in parallel with each other. And on we go. You're not going to find a way to combine any of these resistors. So the best bet is to just make statements based off of Kirchhoff's loop rule and Kirchhoff's junction rules. So step number 1, identify the junctions. So I see the junction here and a junction here. Maybe we'll label these as A and B. What's our next step? Well, you might not like this because it involves guesswork. But we'll say that step number 2 is guess the currents. Now, what do I mean by that? It appears there are 3 ways to get from point A to point B. One way is along the path that includes the 12-volt battery and the 5 ohms of resistance. Of course, another way to get from point A to point B would be on this path that includes the 8-volt battery and the 3 ohm and the 1 ohm resistor. There's yet another way. Okay, so if there are 3 unique paths to get from A to B, then that means there are 3 unique values of current flowing in this circuit. When we say guess, that means guess the direction that the currents are flowing. And we'll label them as I1, I2, and I3. So for example, there's some current that flows through this portion shaded in orange. So what should we guess? That the current we're going to label as I1 flows up through the 3 ohm resistor, or should we guess that the current flows down? Well, I like the first guess. Let's go with that. It's just a guess. We might be wrong. But if we are wrong, we're just going to find out that the value of that current is negative if we guessed wrong. In the end, we'll change our answer to positive and just flip the direction that we guessed. Okay. Now we'll guess the direction of current flowing through the middle branch. And again, I'll guess that the current flows upward. We'll call that I2. And now we need to guess the last current flowing through the branch on the right. I'll tell you what, we're not allowed to guess that I3 also flows upward. Here's the reason why. look at the junction at point A. All three currents are flowing into that junction, and that can't be the case, right? There has to be a balance of current in and current out. So I'm going to guess that the current through the branch on the right flows downward. Okay, so let's get to our third step. Apply Kirchhoff's junction rule. So let's make a mathematical statement. Pick one of the two junctions and say that the total amount of current in is equal to the total amount of current out. So let's pick junction A. So what current or currents are flowing in? I1 flows into that junction. I2 flows into that junction, but I3 flows out of that junction. So we get I1 plus I2 is equal to I3. Okay, well that's three unique variables, but only one equation. So we're going to need two more equations, three equations for three unknowns. So how do we get the other two equations? Well, that comes from step 4, which you guessed it, apply Kirchhoff's loop rule, and I guess 2 times. That just means we need to pick any point we want to in the circuit and go around a loop that brings us back to that point. How about we start here at the lower left corner? Call that point X. So how can I go around a loop and end up back at point X? And by the way, let's get all our currents drawn here. So we have I1, we guessed that that flows in an upward direction. We have this current I2, and we have a current I3. Okay, so that's going to help as we trace our way. So let's, how about I make a loop that starts at point X and goes counterclockwise around this full outside path. All right, so remember how we calculate voltage gains and voltage loss. In any case, we're going to say the overall net change in electric potential around my chosen loop is equal to 0. So the first thing I encounter as I go counterclockwise is this 1 ohm resistor. And the current that flows through that 1 ohm resistor is this I1. That current flows to the left through the 1 ohm resistor, but I'm tracing to the right, so this is going to represent a voltage gain. So we're going to say plus 1 from the 1 ohms times I1, the current flowing through the 1 ohm resistor. Now what's the next thing I encounter as I trace along? Let's see, so we traced here, going. Okay, so the next thing I encounter is this 5-volt battery. I'm going from the positive to the negative terminal, so we're going to say minus 5. Okay, what's the next thing I encounter? It's the 2 ohm resistor. Now what's the current through the 2 ohm resistor? That's I3, right? And I3 we see is flowing to the right, but we're tracing along to the left, so this is going to be plus. We're swimming upstream, so to speak. So plus 2 because of 2 ohms, times I3. Remember, Ohm's law says change in voltage is equal to current times resistance. So it's a resistance of 2 and a current of I3. Okay, the next thing I encounter is the 3 ohm resistor. Again, opposite the direction of the current, so it's a voltage gain. So this is plus 3 I3. No, not I3. That was the current through the 2 ohm resistor. I've crossed this junction at point A. The current through the 3 ohm resistor is this current I1. So plus 3 I1. Okay, the last thing is this 8-volt battery. I'm going from the positive to the negative, so that's a loss in voltage, so minus 8. And I'm back to point X where I started, so I can say that equals 0. There it is. We have a second equation to go along with the first one. All we need is a third equation. Let's pick a different loop. So I get to erase all of this. How about we just focus on this loop? Now, where do we want to start? We can start at any point we want. How about we start here at this point P? And this time, let's trace a path in a clockwise direction. Okay, keep in mind, we've already guessed the currents. We've already stated that I2 flows up through the 5 ohm resistor. We've already chosen that I1 flows upward through the 3 ohm resistor. And we've already decided that I3 flows downward through the 5 volt battery. So as we trace a path clockwise from point P back to point P, what's the first thing we encounter? The 12 volt battery from the negative to the positive terminal. So that's a gain. That's plus 12 volts. Now the next circuit element we'll encounter is the 2 ohm resistor. This time we're tracing to the right. The current flows through the right. So swimming downstream, this means we're losing voltage across that resistor. So minus 2 I3. Okay, the next thing we encounter is the 5 volt battery from the negative to the positive. So this is plus 5. And the last item we'll encounter is this 5 ohm resistor. So this is going to be what? Are we going in the direction or opposite the direction of the current? We're going with the current. So it's a voltage loss. So minus 5 I3. Did you catch my mistake? Yeah, that's no longer I3. I3 was the current flowing in this branch, but we've crossed the junction at B, and now we're on the branch where I2 is flowing. So this is minus 5 I2. We're back to where we started at point P, so that's our net change in voltage, which all has to be equal to 0. Let's rewrite all three of our mathematical statements. There's one. There's another. Oh, that's a little messy, isn't it? We can clean that up. Okay, let's get this last one. Clean that up as well. Okay, now wait a minute. I can combine like terms here a little bit. I got plus 12 and plus 5. So how about I get this in the form AI1 plus BI2 plus CI3 is equal to D. Well, I don't see any I1, so this would be like 0 I1. Then I've got a negative 5 I2, so minus 5 I2. And I've got a negative 2 I3, so minus 2 I3. And then, let's see, positive 12 and positive 5 on this side of the equation would be positive 17. If I brought that to the other side of the equation, this would be negative 17. I like that better. I like that better. So let's get rid of this and keep this as our second equation. So here's equation number 1. Here's equation number 2. And let's also get this equation number 3 in this form. So let's see. Okay, I see an I1 here. So we've got a 3I1. Oh, and there's also a 1I1. So actually I'll combine like terms. Call that 4I1. I don't see any I2s, so I'll say plus 0, I2, and then I see a 2I3, okay, so plus 2I3, and then what do we have? A negative 5 and a negative 8, that would be negative 13, but if I bring that to this side of the equation, it would be positive 13. I like that as my third equation. I'm going to rewrite these three equations one more time. I1, I2, I3, A, B, C, D. How about this? So the first equation I can say is 1 I1 plus 1 I2, and then if I subtracted I3 from both sides of the equation, and this would be negative 1, and all that equals 0. Okay, and then equation number 2, 0, negative 5, negative 2, and negative 17. Of course, what if I had multiplied both sides of that equation by negative 1? Then everything would become positive. Okay, and then the last one here, 4, 0, 2, and 13. So I'm implying the I1s and the I2s. This is really 1 I1, 1 I2, and so on. But I can just write it in a more simplified way if I leave out those I's and just note that they're implied. So we have 1, 1, negative 1, 0, 0, 5, 2, 17, 4, 0, 2, and 13. So you recognize this as a matrix. Now how do we solve these matrices? We just do row reduction. So we keep in mind each one of these three rows represents a balanced mathematical equation. Whatever you do to one side of the equation, you can do to another. So I can multiply by a positive or negative constant. I can add two equations to make a third. So I want to ultimately convert this matrix into a form like this. So let's keep line number 1, 1, 1, negative 1, and 0. What I'd really like is if the terms highlighted in yellow are all zeros. Well, two of them happen to be zeros, that's nice, but the problem is with this item. Okay, so how can I make that into a 0? Well, I guess I could multiply line 1 times negative 4, and then add line 1 to line 3. So let's do that. Let's replace line 3 with the result we get when we multiply line 1 times negative 4 and add it to line 3. So negative 4 times 1 is negative 4. Negative 4 plus positive 4 is 0. Negative 4 times 1 is negative 4, plus 0 is negative 4. Negative 4 times negative 1 is positive 4. Positive 4 plus 2 is 6. Negative 4 times 0 is 0, and 0 plus 13 is 13. Okay, I'd actually be happier if this 5 was a 1. So I could I could just divide everything by 5. Oops. So that's what I'm going to do. I'm going to take line number 2, and I'm going to divide everything by 5. So 0 divided by 5 is still 0. 5 divided by 5 is 1. 2 divided by 5 is 2/5. 17 divided by 5 is 17/5. And you know what? I'd also like it if this was a 0. So what do I do? What do I do? Well, I can multiply line number 2 by 4 and then add that to to line number 3 as a way to replace line number 3. So 1, 1, negative 1, 0, 0, 1, 2 fifths, 17 fifths, 0, right? 4 times 0 is 0 plus 0 is 0. 4 times 1 is 4 plus negative 4 is 0. 4 times 2 fifths would be 8 fifths, and 8 fifths plus 6, well, we'll just write it like that. 8 fifths plus 6. And 4 times 17 fifths, let's see, 4 times 17 is 40 plus 28, so 68. 68 fifths plus 13. Okay. Now, remember, the I1, I2, and I3 were all implied. So this line number 3 is really telling us that 8 fifths plus 6 times I3 is equal to 68 fifths plus 13, which means I3 is equal to 68 fifths plus 65 fifths, all divided by 8 fifths plus 30 fifths. Right, I've replaced 13 with 65 fifths. I've replaced 6 with 30 fifths. So this is, oh, and now everything is fifths, so that all cancels out. So 68 plus 65 divided by 38. Oh, I'm going to need a calculator at this point. So I3 is equal to 133/38, which gives us 3.5. Okay, well, that came out to be not quite a whole number, but close. Now remember what line 2 is telling us. These values of I2 and I3 are implied. So line number 2 is telling us that 0I1 plus I2 plus 2 fifths of I3 is equal to 17 fifths. But we know the value of I3 now is 3.5 amps. So we have I2 plus 2 fifths of 3.5 is equal to 17 fifths. Let's multiply through by 5. So 5I2 plus 7 is equal to 17, or in other words, 5I2 is equal to 10. So it looks like I2 is equal to 2 amps. So now we know 2 of our 3 currents. So now we just need to go back to row number 1, which tells us I1 plus I2 minus I3 is equal to 0. So I1 plus 2 amps minus 3.5 amps is equal to 0. So I1 is equal to 1.5 amps. Let's go back to our original circuit. So now we know the value of I1, 1.5 amps. We know the value of I3, 3.5 amps. We know the value of I2, 2 amps. Now let's double check Kirchhoff's junction rule. What flows into junction A? 1.5 amps and 2 amps. So 3.5 amps flow in, and of course 3.5 amps flow out. And by the way, that I3, that 3.5 amps, continues until it reaches junction B, and then it splits off into I1 and I2. So it splits off into 2 amps and 1.5 amps. So yeah, Kirchhoff's junction rules seem to be holding up. So I think we got this all correct. By the way, the original question here was not to find the current everywhere, but to find what was the power consumption of the 3 ohm resistor. Well, the trick to answering any question you can be given about an electrical circuit is to find the currents everywhere. Because once I know the current, I can easily solve for power, right? I know the current through the 3 ohm resistor is I1, 1.5 amps. So if I want to find power, I have 3 equations to choose from: current times voltage, current squared times resistance, or voltage squared divided by resistance. Now, I know there's 8 volts along the same path as the 3 ohm resistor, but that doesn't mean that there's 8 volts across the 3 ohm resistor. All right? So I don't really know the voltage. It wouldn't be hard to figure it out. In fact, well, I guess I do know the voltage across the 3 ohm resistor. According to Ohm's law, V equals IR. So when 1.5 amps flows through a resistance of 3 ohms, you get a voltage of 4.5 volts. So I could do that. I could multiply a current of 1.5 amps times a voltage of 4.5 volts. But what if I didn't want to solve for that voltage, right? What if I just say, hey, I know the current is 1.5 amps. I know the resistance is 3 ohms. The second equation is the way to go. The power is equal to 1.5 amps squared multiplied by 3 ohms, and we get a power of 6.75 watts. Hey, there we have it. An example of a non-reducible circuit where the only way to solve for the values is by applying Kirchhoff's loop rule and junction rule, and in the end, making the math easy by putting our 3 equations for 3 unknowns into matrix form and doing simple row reduction.